On our way to showing the idea of mathematical induction, there's an important idea called the well-ordering principle, which we're just going to talk about, but it kind of underpins the idea of induction. We'll talk about that once we get to induction and the next topic. But the key to induction is that you're building some machine that you're using to prove some result for all indexed values. But the key is there needs to be some sort of smallest index. We really care about having a smallest index. So let's explore what we mean by that. So here we have a definition. We want to talk about a least element. So that's what we're defining here, a least element. So assume we have some non-empty set of real numbers. Then we say some number in that subset is a least element or a smallest element if for every x that's in A, x is greater than or equal to that minimum m. That's what this is saying. Take any other element of your set. X is not less than, it's greater than or equal to that minimum element m. So here are some examples here. We have the natural numbers or the counting numbers, the integers, the open interval from 0 to 1, so that's all of the real numbers on the number line from 0 to 1, but not including 0 and 1. And then we have the including version with the square brackets. That's everything on the number line from 0 to 1, but including these points. So pause the video now and think about, first of all, do these sets have a minimum element? If so, what is it? If not, come up with a way of proving that there is no minimum element. So try that. Pause the video now and give that a go. Okay, now that you're back, the answer to the first one is, of course, yes. And that minimum element is 1. Every counting number, every natural number, is greater than or equal to 1. 1 is the smallest one. So that one was pretty easy. What about the integers? Well, the integers don't have 1. And how could we show one? Well, let's do it kind of by contradiction. Assume that we have an integer that is the minimum. So it's the least element. But if I subtract 1 from it, well, that's still an integer because the integers are closed under subtraction. And it's true that m minus 1 is indeed less than what we said our minimum was m. So this is a contradiction. So m is not minimal because we found something smaller than it. Okay? For the open interval, 0 to 1, well, let's do this down here. Well, remember, 0 and 1 aren't in your set, so you can't pick 0 as your minimal element. So the answer is indeed no. So let's assume m is our minimal element, and it's in, I want the round bracket there, and the interval from 0 to 1, exclusive of 0 and 1. So let's assume that is minimal. But, well, we can't subtract 1 this time because we'll get outside our interval. But we can divide by 2. So m over 2, that's still in the interval from 0 to 1. If you have some sort of whatever point in here, no matter how close to 0 you get, you can always take half the distance. If this is m, well, m over 2 is going to be half the distance from 0. So that's still in the interval from 0 to 1, and clearly m over 2 is less than m. So this is a contradiction. So this open interval doesn't have a least element. However, the closed interval, I'll do this in blue, I guess, the closed interval does. And of course, that is 0. Take any number in 0, 1 inclusive, it's going to be greater than or equal to 0, since 0 is the smallest thing in there. So that is a least element. Well, let's try this one here. Let's do this theorem. Remember, a theorem is a mathematical result where it's kind of important, so we call it a theorem, and it's always true. We're going to prove this is always true. So we want to show that if there's a set with a least element, we'll call it A, then that element is unique. So that's what we want to show here. And I'm going to show you a particular technique to show something is unique. You pretend there are two of them and show that, well, they must be the same thing. So that's what we're going to do to prove this. We're going to assume that M1 and M2 are least elements. Well, in fact, let's be specific, not necessarily unique. So they could be unique, but they don't have to be least elements. So what does this mean? This means for all x in A, x is greater than or equal to m1, and for all x in A, x is greater than or equal to m2. So, think about this. How can, from this information here, that any x in A is greater than or equal to m1, and any x in A is greater than or equal to m2, how can we show that these guys must be equal? Pause the video and think about that. Okay, now that we're back, well, one of the keys to this, in fact, the key, is that M1 and M2, they're elements of A. Least elements are, of course, elements of the set that they're the least element of. So, but we know M1 and M2 are elements of A. So, if this is true for all elements of A, it's going to be true for a particular one, so it'll be true for M2. So that means, so M2 is greater than M1, so using that inequality there, if it's true for all x, it's going to be true for a particular x, and the particular one is M2. And, well, the same thing here. Let's do the other one. If x is greater than or equal to M2 for all x, then let's say x is M1. It's true for all x, so it's true for a particular value, so it's true for M1. So that's what we're doing here in red. We're just using a particular value because we know it's true for all values. So putting these together, well, we have that M2 is greater than or equal to M1, and M1 is greater than or equal to M2. Well, the only way that that can be true is that if they're the same thing, M1 equals M2. So if we have two least elements, they're equal. So that means, there is only one unique least element. And we're done. And it's a very common technique to show something is unique. Pretend there are two of them that could or could not be unique, and show that if there are two of them, they equal. So that therefore there's only one of them. All right. Sets with the least elements are important to us with this idea of being well ordered. So we say a set is well ordered, a set of real numbers is well ordered, exactly when every subset of it has a least element. So if you take any subset you like, there is a least element. So we have 4 examples here. Let's determine which are least ordered. The first one here, well, we just have 3 integers, no problem. -5 is the smallest one. But that doesn't really matter. You can imagine, take any subset of these guys, and we get that it has some least element. Even if you just pick the subset with 7 in it, then 7's going to be the least element. So this is indeed well ordered. What about the natural numbers? Is this well ordered? And again, the answer is yes. Take any subset you like of the counting numbers, and it's still going to have a least element. Well, let's look at this. This set had a least element, the interval from 0 to 1 inclusive, the closed interval. But is this well ordered? And the answer is no. And why not? And it's because there is indeed a subset inside of here that doesn't have a least element. And we know what that subset is. We know that the subset, the open interval between 0 and 1, is a subset of the closed interval from 0 to 1. Every element in the open interval is in the closed interval because the only points that we're missing here are 0 and 1 themselves. So every number in the interval between 0 and 1 exclusive is in the interval 0 to 1 inclusive. So we know this is a subset. And from the previous slide, we know that this does not have a least element. So that isn't a least ordered set. Okay. Now we have the integers. And of course, well, there's lots of subsets that don't have a least element. And this is false too. And this is since, well, the integers is a subset of itself. And we know that the integers has no least element. In fact, pretty easy to see here. In fact, this is almost a proof of saying if a set does not have a least element, it is not well-ordered. And that's how well-ordered sets work. And then we have the important bit to us, now that we have the idea of well-ordered sets. We have this well-ordering principle. And I'm just going to state this, but it's very, very important. It's the principle that every non-empty subset of the natural numbers has a least element. So we can do something that helps us out even a little bit more. It might come in handy, but not only is it that every non-empty subset of the natural numbers has a least element, but we can even say, instead of non-empty subset of the natural numbers, we can say every non-empty subset of the integers with a least element. So we can even say that instead, and that's a little more powerful. So we can have something like these down here, and these are going to be important to us, and basically just says, well, it's like the integers except we have a lower bound. And these are going to be important for induction for us. So we can kind of start at any least element we like and go up by ones, or twos or threes, whatever. So let me show you an example of what I mean here. So if we had something like z greater than equal to -2, well, this would be the set. Well, it's all elements of the integers that are indeed greater than or equal to -2. So we'd have the smallest one, the least element, would be -2, -1, 0, 1, 2, 3, etc. So these are going to be the sets we're going to consider, things like this, when we talk about induction. But kind of the key is we have some least element that we're going to be starting at. And this idea of the well-ordering principle kind of happens more behind the scenes of induction rather than out in full force. In fact, you can show that this idea of the well-ordering principle is exactly the same as mathematical induction. The well-ordering principle holds for a set if and only if the principle of mathematical induction holds for that set as well. So this is very linked to the idea of induction, which is coming up in the next video, but we're going to kind of use it more behind the scenes than explicitly.